physics and CS, with as much work on quantum complexity theory as from the physics side, and she has lots of work on quantum Hamiltonian complexity, error correction, and so on. And then it's a pleasure to also have Adam Nahum, who is from the École Normale Supérieure. Adam recently won the Philip Meyer Prize in theoretical physics for his work on, which is quite relevant on the dynamics of quantum many-body systems, especially using techniques involving random quantum circuits. So, to kick off the panel, let me just start by putting out a somewhat provocative vision along the, I think that maybe Shivaji had been hinting at, but this is at least the way a computer scientist would look at it. So let me just try to say how I view it. So you might say, well, how would quantum computers be useful? Well, we have several ways we could think of it. One is, well, we are going to solve optimization problems or things like factoring, well-defined computational problems of that kind. The other way we could say is, well, let's go back to the fact that quantum computers would allow you to simulate quantum mechanics efficiently, and that's surely a very important thing to do. So, and what else could there be? Well, there's a third way to look at it, which is, if you look at classical computers, one of the things that they provide us with is an excellent interface to the world. And in computer science terms, we talk about the human HCI, human computer interface. And so, well, if we think about it in the context of the quantum world, then this takes on a completely different view, in the sense that Hilbert space is very large. And the way we could think about it is that our experience of Hilbert space is mediated through whichever parts of Hilbert space are accessible through the fact that they are amplified to the classical world through measurements. And so, could it be that once we have quantum computers, that this allows us to probe parts of Hilbert space that we wouldn't have been able to probe otherwise, so that that our classical experience, which we could think of as an experience of the parts of Hilbert space that we normally have access to, could we actually enhance that by mediating it through a quantum computer? So I know this sounds somewhat but this is one way you could think about this interactive quantum dynamics and say, what can we achieve through this method? So anyway, I'll turn it over to the panelists to take a few minutes to give their thoughts about they may have about Shivaji's talk, and also about anything else they'd like to bring up. So
Umesh, one comment about what you just said. Of course, what the talk that we heard today, which was very nice from Shivaji, is not quite like that, because often we have classical predictions and we come with theories and so on. So we're not entirely open to, we want to have a problem where the experiment is actually telling us, hey, this is going on, and now let's try to explain it better, right? It has to come first from the experiment, and then maybe the theorist will have some classical description of it, right? That would be more interesting.
So you're saying it could be that the phenomenon would actually first come up in experiment before we actually understand it.
Yeah, that would be the more interesting thing. Because now I think, I don't want to do justice to the talk that we just heard. I found it interesting, but it's something where you say, well, we expect maybe something like this, and now we're testing this. But it's not. It's a confirmation. But of course, things get really interesting when the experiment shows up things regularities or patterns that we do not quite understand.
Mm-hmm. But can't that work? work in conjunction in the sense that you sort of say, well, if we look in this direction, we may find something, but then you look for it, you find it, but then you find something else as well. So in other words, where do you look? Where do you start by looking? And so you could sort of say, well, how if we wanted to use, well, first, to what extent is it possible? But then, if you wanted to use quantum computers to mediate the search for sort of, isn't it possible that one could have completely new physical phenomena that were not accessible to us because the normal mechanisms for observation would not have revealed them to us, those phenomena to us, but they're now they might be accessible just because we have an intermediary, which is a quantum computer.
Yeah, I think that's interesting, but maybe some of the other panelists have thoughts on this. Yeah.
I think we are not there yet, but I think.
I'm sorry.
Maybe I can come. First of all, I mean, I totally agree with Barbara, which is that it should be, it's a new physical system and it should do things. The real payoff is going to be to run it in experimental mode, in which you search and hopefully you need some cost function which tells you what's interesting, and then you go looking. So this talk was more to say, the way to look at it is perhaps to say, supposing we had such devices 20 years ago, maybe we would have found time crystals by searching for them on these devices, whereas we couldn't have found them on other devices. So I absolutely agree with what she said. Coming back to what you said, Umesh, I think as a formal matter, right, we're going to be looking at a certain space of evolution, which are made up of this toolkit of unitaries and measurements. Now, the answer to your question is somehow buried in there, which is to say that if you were simulating some aspect of the world which you normally perceive in a certain way, would you perceive it sort of differently if you could do it this way? So I think you maybe have to simulate the world closer to the one we live in, as opposed to but in principle, I think they're the same idea, that ultimately any experiment, any observation, it's start somewhere and you end somewhere, and you do some number of things along the way. So what you're looking for fits in this larger class of evolutions.
Yeah.
Somewhere.
Could I pick up on something Shivaji said at the very beginning? Maybe I can ask you, Shivaji, and any others.
Adam would like to, say something, since he worked on his measurement.
So
what else might be possible?
Sorry. I think maybe I have a lag on the connection or something. So you made a comment at the beginning about you made a contrast between quantum computation and the kind of things we think about in StatMech, in terms of kind of a system which is sort of statistically homogeneous everywhere versus a very highly structured computation. And so I wanted to ask sort of how much, if we want to make a bridge between those things, how much is that a worry? And or might it be possible to put things which are more like real quantum computations in a statistical mechanics language? So, for example, as a question for quantum information people, might it make sense to have sort of random ensembles of algorithms which look a bit more like a StatMech problem, in the sense that we have in many body physics random Hamiltonians, random matrix theory, and we can have random circuits, but presumably that's not anything like what you'd think of as a computation. But is it imaginable that you could have random ensembles of algorithms, so you could start to ask in a statistical mechanics language about generic properties of quantum computations and things like that? Or are you always going to have this problem that Shivaji mentioned, that a real computation of interest is always something specific and structured, and there's a disjunction with the kind of things we think about in StatMech? There's a bit of a vague question, but I just wonder how close do you think?
Is that for me or Shivaji? I'm not.
It's for anyone who.
Okay.
Barbara,
well, I think I can tell from the experience that there is a impact and the community of interest for a given algorithm we do, and then there is a computational complexity of that algorithm. So one time which we did it successfully, the community of interest became very, very narrow. We managed to make bit strings with high fidelity, better than classical computer. So we outperform a classical computer, but the community of interest become very narrow. So I imagine that the next case, we might solve a problem, let's say related to out-of-time order correlation or something, that would have a slightly bigger community of interest or bigger class of group of algorithm. So I think you guys are maybe talking a little more general, that cost functions and algorithm in general. I think these are a little further down the line in the future. But I think very specific cases like time crystals or the group of algorithms or the class of algorithms would gonna very slowly grow, and the community of interest is people who care about those cases are going to very slowly grow. It's not going to be very different than quantum supremacy experiment, which was not, which was highly contrived to beat the classical computer essentially. So I think it would be very similar to that, the next milestone.
Okay.
Maybe as a comment to Adam, I think it doesn't, right? You design optimal algorithms, right? So it doesn't fit very naturally with the statistical picture. Only when you're a very little child do you do random things, but you quickly learn the optimal strategies. And but in that sense, I think maybe machine learning and quantum machine learning, you have some of that, where you can do some statistics, right? But not in the sort of traditional design of algorithms. At least I don't see it. Maybe I can ask a question to Shivaji about his talk or about the field a bit. And this is on the effect of noise and also related to experiments. So, well, you made the point things were done to distinguish the effect of noise and thermalization without, presence of noise. But noise can also be, positive, right? The noise in these devices is not the polarizing noises necessarily. It's actually, if you leave the device alone, most qubits just, go to their ground state, and there's some fluctuations, not entirely true, but not necessarily very high entropy state. So you could also have, why not include the noise in the description of these phases, or are there reasons? So how does the field look at noise or Lindblad equations, so to say, and phases in those systems?
Right. So, actually, Vedika's on the call, maybe able to speak more precisely to this, but in terms of different kinds of noise, because she and Matteo Ippoliti at Stanford did a lot of the detailed thinking. I mean, broadly speaking, experience has been that if you add some fairly general, then the time crystal ceases to be well defined phase. And so now I'm hedging because you raised the question of, could there be some very specific kind of noise which exists in these devices which could still leave you? I know maybe they can speak to it. I know they thought a bit about it. Indeed, when we began the experiment, part of the hope was that the experiment itself maybe tell us that the error model that one really should use for these devices is more specific than the one that was thought of initially. in the quantum supremacy experiment. But maybe if Vedika can jump in and speak to what we learned at the end of the day, that would be great.
Yeah, so I can maybe say two things. One is, indeed, in the MBL problem, where the problem itself has structure, if your noise also has structure. So for instance, in MBL, we have these conserved operators, which mostly look like they're aligned in the Z basis. So if you only had dephasing noise, which coupled to that Z channel, that's in a sense less dangerous than spin flip noise. So there are different kind of differences in that regard, but in this particular platform, there was no reason to expect that one type of noise is dominant over another. So then the depolarizing model works pretty well as an approximation. But then let me give a second answer to that, which is which Shivaji alluded to, which is can we which is the benchmarking business, right? So can we use noise maybe more as a feature rather than a bug, right? So can we maybe, if we wanted to probe the properties of these L bits, for instance, can we it is certainly the case that the effect of noise is different depending on what the intrinsic dynamics in your problem are. To give you an example, if you have some noise in some one qubit, if you're in the localized phase, the effect of the noise acts in time but doesn't really spread out in space. On the thermalizing side, the effect of noise spreads over space very, very quickly, and that is what the supremacy experiment was plugging into. So I think it's a broader question to see, if you have different types of noise, could we use that to characterize the dynamics based on how they couple to the noise? But at least just for the time crystal experiment, there was nothing extremely special there.
But was there a limit? Because the time crystal experiment, with a certain number of rounds, and what if you would gone 10 times longer? Would you, I assume you believe it'd be the same, it would not be over dominated by noise. Is that right? Or is this...
Yeah. So this is, Shivaji didn't delve into this in too much detail, but, one of the, indeed, I mean, you instead of decaying exponentially in the space-time volume, in the time crystal experiment, you're mostly decaying exponentially in time because the effect of the noise is not spreading out too much. So if you wait long enough in a realistic experiment, the signal will go to zero. So some of the things that we did was to employ kind of time reversal protocols to try to distinguish between this intrinsic thermalization and external noise. So, so for instance, what we did is we measured the same autocorrelators, but time evolved with U dagger U, which of course unitarily would be just one. But then what it picks up is more if you get a decay for that autocorrelator that's coming dominantly from the noise, because if it is perfectly unitary, that would be nothing. And in the limit of being deep in the MBL phase, if you kind of divide out the actual dynamics with this kind of normalization factor, you reproduce what you should get to very good accuracy. So what that means is that at some point you're going to hit the noise floor in the experiment. So this division works well on a computer, but there you'll hit numerical precision. In a lab, you'll hit measurement precision. But modulo those things, yes, we could have gone a factor of 2 longer in time and still been able to see something.
Yeah, it's just a signal to noise ratio. You have to average for a long time. And then at some point, we get tired of averaging, essentially.
Maybe I can ask a question of Pedram. So in terms of the platform, I mean, when do you see it being possible to actually feedback, measurements?
Yeah, I don't know. It's hard to make promise publicly, so maybe I should definitely not next year about that. We are focusing on passive error correction currently. For active correction, you have to bring the time of the readout of the qubits much closer to the time of the gate, and particularly on the experiment that you mentioned on your last minute of talk on measurement induced. The current challenge for us is that the gates are about 30 nanoseconds, but the time to measure the state reliably is close to 800 nanoseconds. So, and the feedback and the measurement-induced transition both needs much shorter readout time. And that's a very hard engineering challenge which we are working on. So I think first you would hear from us that we have managed to do shorter readout, and then these feedbacks would follow probably.
So in terms of actually being able to do an interactive experiment, that you would say is a little ways off.
Yeah, I think so. It's certain engineering challenges are really rooted in deep physics that we don't have good understanding from. Yeah.
Sorry, but just pursuing that a little bit about the interactive aspect. So Barbara, you worked on some of the complexity theoretic aspects of interactive, experiments. So can you say a little bit about that? So it's in terms of, well, yeah, I mean, there are various reasons why one does these interactive protocols, but.
Well, yeah, I don't know whether I'm able to comply in the sense that I haven't thought about interactive proof systems, for example, in a while. I more think about error correction these days, and that's there's a lot of you also need interaction, but well, not maybe at the first rounds. You hope to get all the information about errors and then leisurely process this. Yeah, I don't know what to say. I'm actually surprised that you stress this interaction, because a very old-fashioned point of view in quantum information was like, well, if you do a measurement in the middle, you can just replace it by something quantum, and then but of course the point is you're leveraging the power of classical computers in this interaction. Yeah. And that's really the thing that makes it different. Yeah.
Well, I think that's correct. Of course, that goes back to the very early days, when the question came up whether intermediate measurements increase the power of quantum computing. But now there are also these other issues, right, having to do with, well, I mean, you worked on them as well, but in terms of, how do you deal with untrusted quantum devices through interaction? And how do you use it to reach into Hilbert space in ways that you would not be able to do otherwise? And so I think that there's a whole new way of thinking that maybe. Sorry, Aram, did you have a question?
Well, I guess you guys have touched on a lot of this, but. I mean, along with what Barbara was saying about interaction, it does seem like fault tolerance is a very important case here, and it's a situation where errors don't blow up, right? So it's. I mean, people have talked about it in sort of vague terms, in terms of a phase transition, but I guess one interesting thing is that if you have a generic quantum circuit, like one error in the middle will completely randomize the final answer. And in a fault tolerant circuit, it looks very different. One error in the middle will have no effect on the final answer. And one related, so what is the question? One question I have is, should we view random quantum circuits as a toy model for a non-error corrected quantum circuits? And is there any way to sharpen that intuition? Like maybe a non-error corrected quantum circuit where we're just sort of not really trying to do things. Maybe there's some way to compress it so that it really looks even more like a random quantum circuit. Like maybe we're not being as efficient with our degrees of freedom, but there's a way to compress it so it looks nearly random. I don't know exactly what the right questions are there, but it seems like there's a vague intuition there that like we study random quantum circuits because they're a proxy for generic quantum dynamics. And I wonder if there's a way to sharpen that in any way.
Could you say again what it was you wanted to compress? You want to start with a generic random circuit, or you want
a generic circuit. Let's say I have a circuit to factor Shor's algorithm. You do Shor's algorithm or simulate the transverse field IC model on a quantum computer. But there are various tricks that people have to say, well, sometimes we can save a few qubits here. Maybe we can model the circuit as a tensor network, and we find that it's not quite as entangled across this cut, so we could compress this side to fewer qubits. There are various papers about simulating large quantum circuits on smaller quantum computers, and they hit limits when you can say it becomes hard to compress because the amount of entanglement across subsystems becomes nearly maximal. So I'm not quite sure what the right thing is there. I will say, for classical data transmission, there's this sort of heuristic idea that sort of generically, if I'm just typing English, that's not full entropy. But if I run it through a data compression algorithm, I get something that's nearly full entropy. And maybe that's a good starting point if I'm going to try to use to encrypt it in a cryptographic way. This is all very heuristic, but there's a sense that sort of generic data is not, has some entropy, but it's not full entropy, but compressing it makes it nearly full entropy. So, this is extremely hand-wavy what I'm saying, but I wonder if there's any utility to trying to formalize any of it.
Sounds like a sort of RJ-ish idea. You want to coarse grain and sort of flow off to a fixed point. So you want a certain circuit flow off to fully random.
Yeah.
Don't we know that for a generic circuit, you can't compress it very much, that it still has generically it has a circuit complexity which is proportional to its depth, just with a constant which is smaller than one.
Well, this video call, like a generic communication message I cannot compress, but yet this video call is compressed because our faces are not generic images. So that's the intuition of maybe many quantum circuits can be compressed. Another way of saying that is a lot of these random circuits they thermalize to infinite temperature, but things are not always at infinite temperature, and so that's another way in which the theory could be developed a little bit more. I think there are random circuits that have conserved quantity. So yeah, I don't know if that's the right direction.
Sorry, can I just very quickly, Aram, you mentioned sort of in one breath simulating the Ising model or something like that, and a quantum algorithm to do a useful task, a computational task. But maybe the question that many of us statistical physicists would have is, how should we heuristically think of what those circuits which are doing something computationally useful look like? And how do they look different to chaotic evolution of a many-body system? I don't have any intuition for that. It was sort of what I was trying to get to before.
Yeah, it's very complicated enough. Others have insight into this, but just think about an algorithm that multiplies two numbers or does modular exponentiation. In a lot of these, if you have one bit that gets flipped, it's going to affect a lot of other bits. And if it didn't, then you could probably parallelize it. If you have little blocks and each bit in there doesn't affect too many other bits, then that means that there's scope to parallelize it. And that's sort of like why I suggest that if you've taken advantage of all the efficiencies you can, then things, that it may start to look like a random circuit. Even that's the vague intuition behind that.
Thank
AJ,
you.
can I comment on this, or can I maybe pick up on this?
Please, yeah.
Yeah. So maybe an answer and an attempted answer to Adam's question about a random ensemble of algorithms, and basically sending this question to the computer scientists here. So if I take, for example, a piece of quantum material at some reasonable lowish temperature or energy density, and I take it out of equilibrium and I let it evolve in time, then it's going to generate very non-local entanglement, very non-local correlations. It's performing some kind of quantum computation. In the end, we can read off an answer in a set of readout qubits, and the answer will generically be something like, what is the diffusion coefficient of this quantum material, right? We'll get this answer, and we'll get actually the same answer no matter what is the disorder realization in this material, as long as the average disorder is thing. So the question is, in what sense can this be thought of, if we think of this material as a circuit, as a quantum algorithm, as an ensemble of quantum algorithms that give us the same answer, and we can somehow try to analyze it in computer science ways and see if it has it gives a quantum advantage, for example. Is this an example of ensemble of algorithms that we can actually and have actually looked at in statistical mechanics analysis?
Well, I don't want to derail things too much with the compression thing, but one thing you could do in this kind of low temperature setting is you could say, well, suppose the system has some entropy density. Then that means that you can take little blocks and compress them, and maybe you can do the quantum computer could do that fairly cheaply, perhaps, and then the dynamics could be done. Then you could do the dynamics on this compressed space, and then even though the underlying system is low temperature, that would be closer to something where each qubit looks closer to maximally mixed. Now, there's still many steps from there to, like, does it fully look like a random quantum circuit? But that would at least be, getting closer to something where even though you're simulating a low temperature system, you do some fairly mild compression and you get something that looks closer to infinite temperature.
Maybe one comment also coming back to this error correction fault tolerance is that, of course, if you have errors in your circuit, you also have an ensemble of circuits, and if it's fault tolerant and you're below threshold, then it is keeping its functionality, right? But if you're not, or you haven't designed it well, then it's losing its functionality. So I think that's maybe the best example I can think of. That it's
Sorry, there was a related point that for Shivaji, when you spoke about your time crystal experiment, there was something that you brought up which I didn't fully understand. So you said, well, look, normally you would be probing you'd be in an equilibrium phase where you're probing the low energy states, and here what you're saying is you find ordering throughout the Hilbert space, including at your high energy eigenstates. So can you say a little bit more about that, just to
But let me describe it this way. So, this was a Floquet problem, but there's a similar statement. The paper we first wrote, David Hughes and myself and Rahul, and I won't list everybody, Rahul and Kishore. It was called Localization Protected Quantum Order. So that one was actually on the transverse field Ising model with random bonds and random fields. This is actually a very well-studied problem. There was a lot of work on this before we came along. Now, what's interesting is that when you work on that phase diagram using the tools of statistical mechanics, if you say, I'll just take that Hamiltonian and calculate the properties of e to the minus beta h, then you can't find any order at any non-zero temperature, because that's a celebrated theorem in statistical mechanics that you cannot break a discrete symmetry in one dimension above zero temperature. So all you have is what you would call the paramagnet. So, but when you examine the individual eigenstates of the Hamiltonian, going all the way up, in energy, at least in the case which is described by free fermion, that gets more complicated. But it doesn't really matter. The point is, in the statistical mechanical version, what should have happened was that any non-zero energy density above the ground state should have given you no symmetry breaking. And in fact, you get it at non-zero energy densities. And in the special case, you get it at any energy density whatsoever. So that's the case where you have a Hamiltonian. You can be very sharp because you can define the energy density with respect to the Hamiltonian. For the Floquet unitary, right, since it's the unitary, there's not really an energy. So it's sort of but what you can ask is how close you are to a certain kind of state. Maybe, if you start with, let's say all spins up and you get very far from it. But in the case of the Hamiltonian problem, the localization protected order is very striking. It really violates this theorem, which, goes back to Landau, which is that you cannot break discrete symmetries at non-zero temperatures in one dimension, continuous symmetries in two dimension. That's the Mermin-Wagner theorem. And localization allows you to get around it. I don't know if that quite.
I'm not sure I completely understood. So the sense I got was that this was exploring the high energy part of the spectrum, not just the low energy part. So is that to what extent is that unique to this experiment? So is that something that just in terms of probing Hilbert space, so which parts can you probe and not probe in experiments? So can you say a little bit about place this in context? And
sure. So I guess there are two issues. One is as an experimental matter, if I give you a solid, right, and you try and heat it up, it's got degrees of freedom. There's a locally unbounded Hilbert space, so you're going to keep heating, and so there's, in a sense, you don't get to infinite temperature just because things keep happening. Now, if you have a model system which is has a locally bounded Hilbert space, qubits being the extreme example, then of course for spin systems or qubit systems, you can sensibly talk about the sort of configuration which you would think of as being infinite temperature, very high energy, which is hard to do if you can just keep absorbing energy forever. So within this more restricted class of systems, which you either will realize to a good approximation, basically, ultimately anything has degrees of freedom going, out forever. So what you really need is that the local degree of freedom comes with some gap, right? So that you are able to sensibly excite things below the gap and not above it too much. So once you've accepted this locally bounded Hilbert space description, then then there's this distinction between finding interesting things happening for states which are very high energy with respect to a Hamiltonian, and not finding something interesting. So in the traditional understanding of statistical mechanics, you wouldn't expect to find anything particularly interesting because the thermal density matrix at infinite temperature is just e to the minus beta h with beta equals 0. So you're just taking a totally unrestricted average over all states. So in this case, the fact that you can see things in individual eigenstates, ETH is the other way to look at it, which is to say that every individual eigenstate is supposed to reproduce for you the statistical mechanical density matrix. And here, these high energy states don't do that. So they're special states, which is where the localization comes in.
Great. There's one more question from Or Sadat.
Hi, Shivaji.
Hi. Nice
So I also wrote. Nice to see you. So I wrote the question down so it's hopefully clear. TFNP is the complexity class which contains NP problems with the property that every input has a witness. I hope that makes sense. So there are NP problems for which it is guaranteed that there is like a witness that satisfies the problem, right? That's a special subclass of NP. There seems to be a connection to the topic of the talk today, in the sense that in the relevant phase that you mentioned, there is always a periodicity. But I'm wondering if there's hard or interesting computational problem that might be hiding here. For example, finding you mentioned that there's a time limit after which you would get back to your original state, for example. So for example, maybe it's hard to find that time. You also mentioned that there are pairs there. So maybe, given one state, find its, its evil twin, things like that. I'm not sure if the second problem made sense.
I'm actually, I have to say, as I'm reading, I have, as you'll remember from the old days, a very limited understanding of such matters. So I tend to think of a witness mostly as a, so I guess this is the case where a witness is not a solution, and it's still hard.
So maybe, can I translate slightly?
Sure. Go ahead.
So Shivaji, I think correct me or if I'm getting this wrong, but maybe what Or is saying is that, look, you have these systems where you're saying, you're driving them at a certain frequency, but then you see some other completely different period show up in terms of the dynamics. Or there's some other pattern that shows up. So there's some pattern that shows up once you actually do the quantum evolution. And the question is, well, is this something that might actually be hard to find? So in other words, you set up the system and you have no idea what this pattern is, and once you find it, you can verify it and so on. But could it be that these are hard computational problems hiding in the definition of your system?
I mean, it's a really interesting thought, because in terms of using these systems as experimental devices and going hunting for interesting things, I think Or's question would come up, namely, if you saw something interesting, would you recognize it? Right, which is, I mean, physicists tend to have a standard, we tend to think in terms of correlation functions, local expectation values, looking for certain kinds of order. We have our list of things, and you could imagine looking for them. I don't know. I mean,
just like for a concrete example, do you know how hard it is to find the period itself? Like the time in which the periodicity appears?
Again, maybe I'm not getting the depth of your question, but something like periodicity, and you do a Fourier transform and you look for a peak. I mean, generally finding a period in some time series, right, isn't that big a deal, as long as the quantity in whom you're looking for a period is relatively easy to measure.
Maybe, sorry, I think if I understand correctly, Or is asking, so suppose you had a certain experiment in mind. Would you be able to predict what period you should see before you actually perform the experiment, or would it be the experiment that reveals it to you? And that, if you were trying to compute it, especially if you were trying to compute it classically, you wouldn't have a hope. Is that possible in the kinds of systems that you were looking at?
Okay, so let me try and repeat it in a way that I think I understand. So is the question, supposing you had a set of local unitaries, because certainly you need a fundamental period to begin with. And the question is, does the actual evolution show some multiple or some, do something else? Does it break that time translation symmetry in some way? And can you say in advance, I mean, how easy would it be to understand it? I don't know. I mean, it's a good question. I mean, it's because in the limit of a large system, you have it's like a huge Hamiltonian or a huge unitary, right? I mean, it's any naive approach certainly is not going to be. In this case, as Barbara said at the start, we knew what we were doing. You're asking, are there other things? That doesn't seem easy to me. Maybe someone else has an answer.
But the disorder is also important here, right, Shivaji? You have a family of Hamiltonians with this sort of
right,
disorder,
and that's what makes it
average quantities. That's part of the question.
But you don't have to average, because every single disorder realization will eventually show this behavior at long times. But you're going to have to wait a long time before you see it. So that's what the phenomenon is robust. But one reason it's difficult to guess is because it's not something that just stares you in the face when you start. No, it's not a few period phenomenon. It's a long time, large system phenomenon. If there were other things like that, they might well be hard to.
Yeah, actually, that also leads to a question that I had is indeed that, you know, for what other Hamiltonians can one make these predictions? Because, you know, this, of course, is ZZ and then a transverse field that is matching the experiment very well. But are there other candidates that people have been looking at and that are experimentally, you know, close, so to say? Of course, they make small variants of these circuits that are.
I mean, I don't know if another Floquet Hamiltonian very different, which, you know, is predicted to show period doubling. There are other Floquets which show other periods. You know, I mean, part of this class of things. This is the simplest one. But, yeah.
Great. So I think we are approaching the end of the panel period. So if anybody has any quick thoughts on the panel or anything else to add.
Okay, maybe again, since Pedram is here, you mentioned that 800 to 30 nanoseconds of the channel. Can you tell us what the physics challenges are that sort of?
Because there is a qubit and you read out the state by coupling it with a linear resonator. If you couple it strongly, and then you're looking for the state of that resonator to be the frequency, resonance frequency of that resonator shifts a little bit depending on your qubit to be occupied by, is it 0 or 1? Shift that resonance frequency a little bit and you're looking for that shift. So, but since you want to read it out, that's the challenging balance, that if you couple it strongly so you can quickly read it out, but then you decohere your system faster. If you couple weakly, then you have to integrate for longer time to recognize how much the resonance frequency have shifted. So that's the challenge. And is a big challenge for error correction, but for NISC, usually when you have measurement at the end, it's not a challenge. Yeah, I mean, it's a major challenge for feedback. But I hope we can come up with lots of exciting physics that you just need to read the states of qubit once at the end.
Great. Well, maybe, yeah, we can, you know, that was possibly this is a good stop. So thanks, everybody. Thank you especially, you know, Adam, Barbara, and Pedram for being on the panel. And thank you, Shivaji, for a very stimulating talk. And of course, thanks to the audience for great questions.
Thank you for inviting us all to join.
Thank you very much.
Yeah, thank you.
Thanks, everyone.
Thanks a lot. Thanks. Bye. Bye.